Sorry.
Good evening,
Yeah,
everyone.
please start.
Good evening, everyone. My name is Aaron Damo. I'm presenting on the topic sustainable synthesis of seaweed-derived electrode materials for supervisory applications. My supervisory committee consists of Professor Kojo Mensah-Dakwa, Professor Anthony Andrews, Dr. Frank Ofori and Jima, and Dr. London Bologa. The outline of my presentation consists of the introduction, problem statements, aims and objectives, methodology employed, results and discussions, conclusions and recommendations, and references. The over-reliance on fossil fuels is driving the need for clean energy and effective energy storage. As a result, supercapacitors, which are considered as one of the best energy storage technologies due to their high power density, relative high energy density, long charging and discharging, their fast charging and discharging, long cycle life, have been considered as one of the best energy storage technologies. However, the adoption of supercapacitors is limited due to the degradation of some of the electrode materials that are employed for supercapacitor technologies. There are some electrode materials like transition metal oxides. When you employ the bioxidant potentials, they tend to degrade. As a result, there is a need for developing more efficient electrode materials for better energy, better supercapacitor performance. Supercapacitors are divided into EDLCs and pseudocapacitors based on energy storage mechanism. Transition metal oxides, specifically manganese oxides, are a type of pseudocapacitive materials due to the fact that they undergo redox reactions. Manganese oxides are excellent supercapacitor electrode materials due to the fact that they are non-toxic and they have high theoretical capacitance. A special type of manganese oxides are trimanganese tetraoxide, that is Mn3O4 materials. These materials are very excellent because they are more stable than the other types of manganese oxides, and they also have double valence states. Because of this, they tend to be very effective when applied as pseudocapacitive or supercapacitor electrode materials. Another type of materials that are employed for supercapacitor applications is carbon-based materials classified under EDLC materials. However, carbon-based materials tend to have limited specific capacitance and energy densities because these materials basically depend on EDLC mechanism to store energy, and as a result they are limited. However, because of this limited nature of these types of carbon materials, there is a need for more advanced carbon materials like carbon conductors that tend to store energy in addition to the EDLC, but also some pseudocapacitive traits. Problems statement. Now, my work is concentrating on Mn3O4. Mn3O4, despite its advantages, has certain limitations. It has intrinsic low conductivity, it is structurally unstable, it is chemically unstable, and as a result, its application or adoption is not very widely adopted because of some of these limitations. And as a result, my work comes up with a strategy whereby we integrate that Mn3O4 with carbon conductors to be able to enhance its performance using green synthesis technology. And also another challenge when it comes to the synthesis of electrode materials is the use of harmful chemical substances and also the use of energy-intensive procedures. However, our method is using very minimal energy-intensive processes and also the use of minimal amount of chemical substances to be able to make our work sustainable and green. So we are using the biomolecules that are inside seaweed and also using the salt of manganese oxide to be able to use these biomolecules in seaweed to reduce them to synthesize manganese oxide for supercapacitor applications, which is very sustainable. And also another challenge is seaweed. Seaweed is a very big problem in Ghana here. When you go to the coastal regions, they are everywhere, causing environmental pollution and also affecting some of the activities that are in these locations. And as a result, my work is focused on making use of these seaweed that are causing too much havoc in these environments and putting it into a material of use, converting it from a bio-waste material into a material of benefit to the people. The aims and objectives of my work. This study aims to develop and evaluate Mn3O4 nanoparticles and a composite of the Mn3O4 nanoparticles and activated carbons, all derived from these seaweed, from the same seaweed biomass. And the specific objectives include to synthesize and characterize this Mn3O4, to synthesize and characterize another composite of the Mn3O4 with carbon conductors derived from the seaweed using green synthesis problems, to fabricate and evaluate a symmetric supercapacitor device from the nanocomposite electrode material, and to synthesize and characterize activated carbons. So the methodology for the preparation of the MM304 using the seaweed extract. So we take the seaweed extract, we clean it, and then we boil it at 80 degrees Celsius for 4 hours. The extract that we got there, we dilute it, and then we take 20 ml of that, and then we add 0.1 grams of KMNO4 to it. Then we put it on the hydrothermal process for at 140 degrees Celsius for 6 hours. That's what we did. And then we put it on the centrifugation, we wash it, and then we dry it, overnight. So that is how we prepare our electrode materials. And then for the nanocomposite, we take 25 ml of the seaweed extract, and then we added it to 50 ml of manganese sulfate, of course 0.1 moles per dm cube. And then we stirred it under ambient temperature. Of course, we adjusted the pH to pH 8 using dilute amount of sodium hydroxide. And then that is, we introduced the carbon quantum dots. Of course, the carbon quantum dots has been enhanced before its introduction. So we added 10 ml of the carbon quantum dots to it. So as you can see, the color changed from the yellow color of the seaweed extract to the dark brown color for the one with carbon quantum dots, and to the light brown color to the one without carbon quantum dots. These were the machines instruments that we used. We used XRD, electrochemical working station, and we also used the particular design as our electrochemical cell there. For the first work, we synthesized the green synthesis, the manganese oxide from seaweed, and then we characterized its electrochemical performance. So for the UV analysis of the MM304 that we synthesized, as you can see, we have 2 peaks here. These peaks are indicating to us that we have synthesized the MM304, as they are an indication of the transition of electrons from the oxygen anion to the manganese cation. Then we calculated the band gap there using tau prod, which is equal to 2.1 electron volts, and we did XRD here. This XRD reflection, the Bragg reflections that we see here are corresponding to COD 10, 11, 26, 2. That tells us that we have synthesized the manganese oxide that we want. For the mechanism, we take the seaweed extract. The extract that we have, it is containing some of these phytochemicals that you see here, and then we introduce the KMNO4, which is a strong oxidizing agent. So the moment it comes in contact with the phytochemicals that are oxidized already, the electrons from it reduce the Mn7 plus, and then it goes to produce the lower oxidation states, which is our Mn2O4. So that tells us that is how the mechanism involved, our proposed mechanism. For the FTIR analysis we did to confirm that we have synthesized the manganese oxide. As you can see, the bands below 700 tells us that these bands are due to the MNO stretching vibrations inside our material. And then the bands at the higher wavelength ends tells us the other functional groups that are present, either due to water molecules or due to the phenols that are from the seaweed. Here, this other seaweed is telling us that we wanted to see whether the seaweed extract contains the phytochemicals. So we did FTIR analysis, and these bands are corresponding to the functional groups that are present inside the phytochemicals that are responsible for the reduction. For the cell analysis, as you can see, we conducted cell analysis towards the surface morphology of our material. As you can see, the particles are well aggregated together. Even though when we go to higher magnifications, it tells somehow so we have a level of porosity in it. So we did EDS analysis to show the elemental marking of our material, the EDS marking of our material, and we confirmed that manganese, oxygen are uniformly distributed, and also carbon. The carbon there is because of the source of the reducing agents, which are basically carbon materials. For BET analysis, we did BET analysis. We have a type 4 isotherm. The hysteresis loss that you see there is indicated to us that there is some level of porosity in our material, and the BGH confirms to us that okay, this particular porosity is a mesoporous material because it is not above 50 nanometers and it is from 2 to 18 nanometers there. That tells us that it is a mesoporous material. We did electrochemical analysis. The electrochemical analysis, as you can see in A here, we have an electrocatalytic oxidation, a strong voltammetric response. That tells us that this particular material has potential for electrochemical applications. And then we check what happens when we increase the scan rate. Then we can see the anodic peak increases as we increase the scan rate, and the cathodic peak also increases as we increase the scan rate. That tells us that okay, this particular material, alright, it has some level of resistance in it. And also we can see that the separation peak potential, the separation potential between the peaks here is almost 94 millivolts. That tells us that the material is a quasi-reversible process that is happening here. It's not completely reversible. So we also did to be able to determine whether it is the mechanism that is involved in our material is basically pseudo-capacitive, or is it a diffusion control mechanism or a capacitive control mechanism. We did this, the power law principle, and then the slope that we go there is 0.6. So this tells us that our material is basically a diffusion limited process. And here we use Dun's method to be able to determine the percentage contributions to pseudo-capacitive or diffusion control or capacitive control. And then as you can see, when we increase the scan rate, the capacitivity increases. However, overall, the pseudo-capacitive or the diffusion control mechanism dominates. We also did EIS analysis to be able to bring the resistive elements. As you can see, for the RS or ESR, we were able to get 2.28, and then also we were able to get some kind of a semi-cycle there in the middle range, and in the low frequency range, in the low region there, we were able to get a linear plot there, which is telling us that our material is basically pseudo-capacitive and it has a limited level of diffusion resistance. And we did the border plot there, and you can see the impedance above 3, which is a bit high, and also the first angle that you see there, which is around 71 degrees, tells us that our material is a pseudo-capacitive material, confirming the observations we did. So for the second work, we were able to synthesize the nanocomposite. So the nanocomposite we synthesized, we characterized it using UV analysis. This UV analysis is for the carbon quantum dots. So the first one that you see there is 200 degrees Celsius for 10 hours. That is our best performing material, and we were able to get the lowest band gap at around 3.55. That is why we use that to modify or to enhance our material. So when we added it in the bead diagram that we see there, bead figure that we see there, we realized that it quenched the manganese oxide, telling us that okay, your carbon quantum dot has successfully combined with the manganese oxide. And also we calculated the band gaps of the two. The one with carbon quantum dots, of course, has a higher one, 3.2, compared to the one without carbon quantum dots, which is 2.73. So we also did XRD analysis. XRD analysis was conducted. The one with carbon quantum dots, as you can see, is very crystalline. We have well-defined peaks here. They are sharp and well-defined, compared to the one without carbon quantum dots, which are broad and not well-defined. We did FTR analysis. The FTR analysis also confirms to us, if we check the lower wavelengths there, that is a confirmation that we have synthesized a manganese oxide. And also if we check in the higher wavelengths, we realize that we have some peaks here, or we have some bands here that are indicating to us that other oxygen containing groups are also present, like the carbonyls and the carboxyls, especially one around 3000, which is due to the hydroxyl groups. We did the frontier molecular orbital theory to be able to determine the band gap. As you can see, the one with carbon quantum dots has a larger band gap compared to the one without carbon quantum dots, compared to the one without carbon quantum dots, telling us that why it is more stable than the one without carbon quantum dots. For SEM analysis, the one with carbon quantum dots, as you can see, the particles are dispersed and fully formed. The one without carbon quantum dots, the particles are not fully formed. There is a level of necking, and also they are very aggregated together. And then we also did EDS mapping. The EDS mapping tells us that the carbon, manganese, and oxygen are uniformly distributed. And for the one without carbon quantum dots, of course, we have no carbon there, and also they are uniformly distributed. We did electrochemical analysis of our modified materials. For the one with carbon quantum dots, you can see that the voltage window expanded significantly, and also the current response is higher at 5 millivolts per second. We did GCD analysis. The GCD analysis shows us a higher discharge time compared to the one without the carbon quantum dots. And we calculated the specific capacitances. The one with carbon quantum dots is 1042 farad per gram, and the one without carbon quantum dots is 41.6 farad per gram. So it was the difference in the behavior. We did EIS analysis of the materials. As you can see in the table here, the resistance values are lower for the one with carbon quantum dots compared to the one without carbon quantum dots. And also you see the impedance is lower for it compared to the first impedance we saw, which is around 3, this is around below 2.5. Same was that it has less resistive elements than the one without carbon quantum dots. We did this analysis to be able to see the complex capacitance. As you can see, stability in our material, the one with carbon quantum dots, but the one without carbon quantum, there is no stability as we increase the scan rate. That tells us there is more ion accessibility and also more charge retention. And here you can see that the energy loss is higher for the one without carbon quantum dots compared to the one with carbon quantum dots. We fabricated a symmetric device, and then we decided to determine the best voltage window for our device. So it was based on the one without no current saturation. So we used 1 volt, the one with 1 volt from minus 0.7 to 0.3. And then we use that particular voltage window to be able to determine its electrochemical behavior. As you can see here, as we increase the scan rate, the material, the electrochemical behavior was maintained based on the shape of the cycle, the CVs. So it maintained its shape, which is telling us that this is an excellent electrochemical material. We also did GCD analysis, which shows a very minimal voltage drop and also a quasi-triangular behavior, an indication of a very good electrochemical behavior. We calculated their specific capacitances and also the energy and power density. For the specific capacitance, 163.4 farad per gram. The energy density for the device is 5.67 watt-hour per kilogram, and then the power density at that energy density is 249 watt-kilogram. So for the specific the stability of the material, initially it dropped. However, it maintained a plateau for 1,000 cycles at 88.2% capacitance retention after 1,000 cycles. For the EIS analysis, we conducted an EIS analysis and we also did an equivalent circuit model to be able to determine the behavior of the material. As you can see, the RS is very low. There is limited amount of solution resistance there, but the charge transfer resistance is around 27. For the diffusion resistance, because the material is completely diffused and limited, it is almost 0.0888. That tells us that our material is very good and it has limited amount of resistances. For the CPE that you see here is because of the porosity of the material. So that tells us that the material is also very porous. And when it comes to the mechanism of charge storage, here we did the power law here, similar to the first one we did, and you can see the B values that we obtained, they are almost equal to 0.5. That tells us that our material, the charge storage mechanism is basically pseudo-capacitive or diffusion limited process. And then we decided to use Boone's method to be able to calculate what happens to the contributions as we increase the scan rate, which is the capacity increases as we increase the scan rate, but overall the diffusion limited process is more significant. So the conclusion of my work, we have been able to synthesize manganese oxide successfully from seaweed extract. We have been able to enhance its performance by combining it with carbon contouring dots, which also gave us a very significant performance compared to the one without carbon contouring dots. As you can see, it's almost 1,042 farad per gram. The one without carbon contouring dots was around 41.6 farad per gram. And then the stability of the material was determined by checking the band gap, 3.2 electron volts. For the one with carbon contouring dots. And then we have also been able to successfully devise a symmetric device, and we were able to determine its energy and power densities to be these values. For the recommendation, to perfect and modernize locally available techniques, which is very important, and the government and higher education institutions should encourage and provide incentives for research. Researchers should be able to encourage to develop more innovative ways of making use of our waste materials instead of just allowing them to lie down there. Future research should focus on the green synthesis of carbon-based materials. Instead of carbonizing with high temperature and dangerous chemicals, how about we use more benign methods to be able to do this? Future studies should focus on isolating, to be able to identify some of the phytochemicals that are responsible of reducing these metal salts that we use in this synthesis. That will be also very helpful. And then the green synthesis should be taught in schools. Students should be taught about these things. They should not go up to a particular level to be introduced to this. But in their high school levels, they should be taught about some of the sustainable ways of developing chemicals or conducting experiments, so that they can be able to know that there are better ways of conducting experiments that will not affect our environment. These are the references that I use. Thank you very much.
All right.